Hi, Assalamualaikum and good afternoon. Today we are having my lecture 15 for CHM477, Inorganic Chemistry, and lecture 15 covers bonding in coordination compounds and how that is explained through crystal field theory. Because in my lecture 14, I explained about valence bond theory, and in this lecture, the next one, which is lecture 15, explanation about crystal field theory. Now, as you can recall from valence bond theory, you could explain the magnetism of coordination compounds, but you couldn't use that theory to explain the colors of coordination compounds. So we are exploring crystal field theory to try and describe how is it that all or almost all coordination compounds are colored, having good colors or good or bad color. Okay, a satisfactory theory of bonding in coordination compound must account for properties such as color and magnetism. Just color and magnetism, as well as the stereochemistry and the bond strength of the compounds. No single theory as yet has been able to do this for us, but rather several different approaches have been applied to transition metal complexes. So today I'm going to explain only one crystal field theory, because CFT can account for both the color and the magnetic properties of coordination compounds. Now, CFT was developed in the 1930s to describe the electronic structure of metal ions in crystals when they are surrounded by anions, or when they are surrounded by electron-rich moieties like ligands. In an isolated metal atom, when the metal atom is isolated, no ligands around it, all the 5d orbitals are degenerate. Degenerate means they have exactly the same energy level. So when you draw the 5d orbitals of transition metals, you draw them all in the same energy level, like I explained in my previous lecture. Now, crystal field theory states that in the presence of ligands, and ligands are treated as negative point charges, ligands are treated as negative point charges. When these ligands approach the metal, the 5d orbitals of the metal atoms no longer become degenerate. They are no longer degenerate. The degeneracy is removed because the magnitude of repulsion between your ligands, which are the negative point charges, and the different orbitals, which are different orientation in space, they are different. The how much the ligand is repelling each one of the orbitals are different. So different degree of repulsion makes the 5d orbitals having different energy levels, because some will be pushed quite a lot, some will be pushed a little bit. So that will make the energy levels become different. The positive metal ion is attracted to negative charges, which are the ligands, but electrons in the orbitals are repelled by the ligands. Despite being positively charged, the metals still have electrons in it. The metal ions still have electrons in them. So the electrons in these metal ions are repelled by the electrons of the ligands. So the repulsion between the electrons in the metal ions and the electrons in the ligand create a change in energy level of each of the orbitals. So thus, although there is an overall attraction, the d orbitals no longer have the same energy level. Now we will begin our discussion of crystal field theory, CFT, with the most straightforward case, which is the complex ion having octahedral geometry. So when I was explaining valence bond theory, I also started with octahedral because octahedral is really quite straightforward. It is the most symmetrical, geometry. Now with CFT, crystal field theory, I'm also going to start with octahedral geometry. Then once you understand CFT for octahedral compounds, we will see how that can be applied to tetrahedral compounds and square planar compounds. Okay, let's start with octahedral field. Now, I'm sure you can recall the 5 d-orbitals. Yeah, you have dxy here. Excuse me, it's moving. You have dxy here, and then you have dyz, and you have dxz, and you have dx squared minus y squared, and you have dz squared. Yep. So I'm sure you recall my explanation on the shapes of the d orbitals. Now the dxy, dyz, and dxz are orbitals that have the lobes pointing between the axes, between the x, y, and z axis. So the lobes are not sitting on the axis, whereas the dz squared and dx squared minus y squared are orbitals that have the lobes pointing directly on the axis. So if you have a look at this picture here, yeah, this is moving. This is the picture of dz squared, where the lobes of the dz squared is directly pointing on the z orbital. This is the picture of the dx squared minus y squared, where the lobes are pointing exactly on the y and the x axis. And these two are very different from the dxy, where the dxy lobes are pointing between the dx and the dy orbital. Dyz, you can see the lobes are pointing between the axes, and the xz also the lobes pointing between the axes. And because of the orientations of these lobes, the interaction between the electrons living in 5 different orbitals will be different when they are repelled by the electrons in the ligand. Now, the EG orbitals are pointing directly at the axis where the negative point charges or the ligands are located. Remember, the ligands of octahedral will be seated here, 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 there, and there. And these ligands interact directly with the lobes of your dz squared and dx squared minus y squared. And because they are directly located on the lobes or on the axis where the lobes are, these two orbitals, these two d orbitals, are experiencing a repulsion that is big compared to the 3 down here. The 3 down here have lobes pointing between the axes or pointing a little bit away from the ligands where the ligands are sitting. Here, the ligands are here. Can you see? The ligands are here, but the lobes are in between. So these 3 different orbitals of D are experiencing a smaller repulsion from the ligand. And these two, in terms of collective name, they are termed the EG orbitals, and these three are termed the T2G orbitals. And the T2G and the EG orbitals are given because of the mechanical quantum, the quantum mechanics that are applied when calculating these things. Just accept for now that these three as a group, they are called the T2G orbitals, and these two as a group, yep, these two as a group are called the EG orbitals. The EG orbitals experience a bigger repulsion when they interact with the ligands because they are closer to the ligands, whereas the T2G orbitals experience a little bit smaller repulsion when they interact with the ligands because they are slightly away from the ligands. So the difference in the magnitude of interactions between the T2G and the EG will remove the degeneracy of these 5 orbitals. They are initially in the same energy level, yeah, if you can recall. So one is repelled quite a lot, so it goes up. Another one is repelled a little bit. It goes up also, become less stable, but now they are no longer at the same energy level. They are having the degeneracy removed. This is your dxy orbital sitting here on a lower energy level. This is your dxy, which is the T2G, and this is your EG orbitals. Yeah. Now, as a result, the EG and T2G sets of orbitals are split. The T2G lower and the EG higher energy level in the presence of 6 ligands arranged in the octahedral manner. The separation between the two sets is given the symbol delta oct, OCT for octahedral. Delta is the energy difference. So the energy difference between the EG set and the T2G set is given the symbol of delta octahedral, delta OCT, or it is also given the term 10dq, which means it is for 10 times the differential in quanta. This is note. I put an additional note here, which is not in your copy. The term dq was derived, this is just an additional information, derived from quantum mechanic description of electrostatic model of the crystalline field. D means deci for 10, Q means quanta of energy. So the energy difference between the T2G and the EG sets is deciquanta. It means 10 quantum of energy. So what does that mean? This is what it means. Okay. This is when you have your d orbital, when you have your metal away from any ligands. The ligands are nowhere to be found. The metal atoms are seated, and the d orbitals are degenerate like this. Degenerate d orbitals in the absence of ligands. Oops, undo. Yeah. And this is this is what happens on the average potential energy of the d orbitals raised in the octahedral ligand field. When the ligands are approaching, remember, ligands are negative point charges. Metals have electrons in them. There are some kind of repulsion between them. So when the ligands are approaching, you have all these degenerate d orbitals become destabilized. When it goes up here, it becomes destabilized. There is some kind of repulsion going on. And then when the ligands come more closer, when the ligands are actually attached to the metal, as you can recall, your T2G are repelled slightly, your EG are repelled higher, so you have the T2G having different energy level than your EG orbitals, and this difference in energy level is called delta octahedral. You will also see later you have delta tetrahedral and you have delta square planar, but for now we're concerned about delta octahedral because we are discussing octahedral geometry. So you have this the d orbitals, 3 of them, dxy, dyz, dxz, which are the T2G group at a lower energy level, and 2 orbitals, which is dz squared, dx squared minus y squared, which are the EG levels, are higher, the separation between the two sets is called delta, and the total of this is 10 dq, 10 deciquanta dq. Now, sometimes depending on the ligand, this delta is small. For example, if it is water, the separation is small. But if it is cyanide, the separation is big. Yeah? Delta, when you have water as a ligand, is small. Delta, when you have cyanide, the delta is big. Yeah? The ligands interacting strongly with the metal ion d-orbital, such as cyanide, produce a larger delta than those interacting weakly, such as water. So water is interacting quite weakly to the metal center compared to cyanide. That is why delta for cyanide is bigger than delta for water. Now, the splitting of orbital energies is called the crystal field effect. Yeah? This splitting is called the crystal field effect, and the difference in the energy between the Eg and T2G sets is the crystal field splitting energy. Yeah, the delta is the CFSE, crystal field splitting energy. Different ligands create crystal fields of different strength, thus the d orbital energies to split to different extent. So, strong field ligands such as cyanide lead to larger splitting energy. Weak field ligands such as water lead to smaller crystal field splitting energy. Now, water is a weak field ligand, Cn minus is a strong field ligand. This is shown in this figure here. Yeah, this is your water. The halogen ions are the weaker, the ligands with very located in the weaker field, whereas your carbonyl in the stronger field. In the middle, you have water, thiocyanide, amine, ethylene diamine, nitro, cyano. So you have increasing what's called the spectrochemical series. So this is the spectrochemical series. The magnitude of the splitting directly affects the color and magnetic properties of the ligand. Yeah. As you can see here, donor atom from group 7 is in the weakest field, followed by the donor atom from group 6, oxygen, followed by the donor atom from group 5, nitrogen, and donor atom from group 4, carbon. So the delta is small by the weak field ligands, the delta is big by the strong field ligands, and I'm going to explain what it means by high spin and low spin later when we talk about magnetism. Yeah. So this is called the spectrochemical series. Yeah, ligands that are put in the spectrochemical series. So group 7 ligands, group 6 ligands, group 5 ligands, and group 4 ligands. The group 4 ligands are the stronger field ligands, whereas the group 7 ligands are the weaker field ligands. Yep. So splitting caused by your iodine will be smaller compared to splitting caused by your carbon monoxide or your carbonyl. Okay, so that is about the splitting of the d orbitals in the octahedral field, and the magnitude of the splitting depends on the type of ligand. If you have the same metals interacting with different types of ligands, then you have different delta values. Yeah. Now I'm going to go into tetrahedral field next. Yeah. If previously in the octahedral field we deal with 6 ligands, and the 6 ligands are arranged octahedral in an octahedral manner around the compound around the metal center. In tetrahedral compounds, you have 4 ligands, and the ligands are arranged in the tetrahedral manner. You all know what the shape of a tetrahedron is. There is an angle of 109.5 between the bonds in the tetrahedron. Now, the interaction between these negative point charges, remember the ligands are negative point charges, and the Eg and 2G are reversed when compared to the octahedral case, because the negative point charges in tetrahedron are not pointed directly at the axis, unlike the octahedral. In the octahedral, the ligands are directly on the axis, whereas in tetrahedral, the ligands are in between the axis. So if you look at this picture here, these are the axis, the lines in black, and you put a tetrahedral arrangement between it. In that picture, you can see very clearly that this corner of the tetrahedron is not on the axis, neither is this corner, neither is that corner and that corner. They are all existing between the axes. So guess who is affected the most now? EG or T2G? Obviously, the T2G will be affected the most, because the T2G, which are the dxy, dyz, and dxz, have lobes pointing between the axis, and that is where the tetrahedral ligands are sitting. So now for tetrahedral case, your T2G is repelled more than your EG orbitals. That is why your EG orbitals is down here, whereas your T2G orbitals are up here. Yep, the reverse is true for your tetrahedral when you compare to your octahedral. And because there are only 4 ligands in tetrahedral, no matter how strong the ligands are, how strong field the ligands are, this delta tetrahedral will always be smaller than delta octahedral, because delta octahedral is caused by 6 ligands doing repulsion, whereas delta tetrahedral, you only have the action of 4 ligands. So delta tetrahedral for the same metal and the same ligand is always small compared to delta octahedral. Yeah, and the orientation of the repulsion is opposite to that of octahedral, where your dxy, dx squared minus y squared, dz squared, which are your EG sets, are lower compared to your T2G set. So that is the case of tetrahedral. So I hope that is clear, because I'm going to go next into square planar. Now, if you look at this picture, this is 6 ligands, situation where 6 ligands are attached to one central metal atom in the octahedral manner, 2 on the x-axis, 2 on the y-axis, and 2 on the z-axis. To make a square planar complex, all you have to do is pull away the ligands sitting on the z-axis. You remove the ligand sitting on the z-axis, and you are going to be left with a square planar arrangement. Yeah. So what happens when you remove the ligands that are located on the z-axis? So those orbitals that has something to do with z will become stabilized. That means there is nothing doing any repulsion with them. Yeah. So any ligand or any orbital that has z term in it will become stabilized. Stabilized means it becomes lower in energy. So if let me do this. Maybe you can see it better. make this comparison so easy for you to see. Huh? What does it do? Excuse me. Yep, like that. So that is your octahedral. Oh, yeah. I'm trying to do this in size, but never mind. Yeah. So this is the situation. This is the situation of octahedral, which you have understood. But when we pull away the ligands that are seated on the z-axis, I told you that you are making any orbital with z term to be stabilized or going to lower energy level. So here is your dz squared, which has z terms attached to it. Yeah, z terms. So this dz squared is going to become very much stabilized. Your dx squared minus y squared is still on the same energy level, but your dz squared goes down quite far, become more stabilized. And this is your T2G in your octahedral. The dxy still remain there undisturbed, but the orbitals with the z term, which is dyz, dxz, will experience stabilization. So all these orbitals, yeah. I don't know whether you can see my cursor moving, so I'll repeat. So this is your splitting for octahedral. When you remove the ligand attached to the z orbital, this dz squared will become lower in energy. It will go lower in energy, which is there. And this is your T2G, where the dyz and dxz also having the z term will become lower in energy. So can you see that all the orbitals having z terms become significantly stabilized in the square planar field, whereas the dxy minus y squared, dxy, they are still sitting in the octahedral position like before because they are still there. Nothing changed, only the z terms are changing. So, excuse me. So, this is the crystal field splitting for square planar field. Yep, derived from the octahedral field. You have your square planar field. This is the crystal field splitting for your tetrahedral field, and this is your crystal field splitting for your octahedral field. So, yep, I have summarized everything. A square planar arrangement can be obtained from an octahedron by removing the ligands located at the z-axis, as I explained earlier. Therefore, the crystal field orbital splitting can be derived from that of the octahedral. The diagram below illustrates the differences between the three crystal field d orbital splittings as compared to the isolated metal atoms. So I'm making everything all in one page now. I'm making you dizzy. Okay, there you go. Okay, so in summary, you have this as the degenerate orbitals can be drawn either as straight lines all in the same energy levels like that, or you can stack them up. You can stack them up closely. Stack them up closely to show that they are degenerate or they are at the same energy level. So these are excuse me. So these are your I'm having problem pointing this. So these are your d orbitals before any ligands approach. So it is sitting pretty at the bottom here. When 6 ligands come to make an octahedral arrangement with that metal, this is what happens. You have your Eg become more destabilized compared to your T2G. Yeah, your Eg here is more destabilized compared to your T2G, and the splitting is called delta oct. When you want to see what happens in square planar, you start with your octahedral arrangement, but the dz squared will become very destabilized. It goes down there. From here, dz squared in octahedral was here. It becomes destabilized to go down there, whereas your dx squared minus y squared remain where it is. This is your T2G. You have dxy, dyz, dxz. Anything that has z, two of them will also become stabilized to go down lower, but your dxy remains at the same energy level. So this is the splitting for your square planar field, whereas down this way is the splitting for your tetrahedral field, where your Eg orbitals are repelled a lot less compared to your T2G orbitals, because in tetrahedral arrangement, the ligands are located between the axes, and I was telling you about the magnitude of delta. Delta tetrahedral is smaller compared to delta octahedral, and in calculation, delta tetrahedral for the same metal and the same ligand will always be 4/9 of delta octahedral. Yeah, because it is delta tetrahedral is smaller than your delta octahedral, because only 4 repulsion happening here, whereas for octahedral there are 6 repulsions happening. So this is a picture summarizing my lecture, lecture number 15. I think, yeah, lecture number 15. I'm going to stop here for lecture 15. Half an hour would be good enough for you to digest the information. So I hope you understand how the crystal field splitting energy come about, what are the things that to look out for your octahedral, for your square planar, for your tetrahedral, and also for the magnitude of repulsion caused by different weaker or stronger field ligands. So that's it. Thank you very much. I will see you in my lecture 16, where I'm going to be using the crystal field splitting to explain colors. Yeah, to explain colors. So that's it now, everyone. Thank you very much, and I will see you in the next one. Keep safe, study well. Assalamualaikum.